Okay, so stochastic calculus course number 3. Okay. So during the previous session we have spent time on conditional expectation. I will remind basically the definition quickly here. And then we are going to finish to prove a statement I have given to you during the previous session. And a little result concerning Gaussian vectors and conditional expectation. Okay? So, first, I remind you the definition. So, I have my initial probability space. So, just a remark, I will be able to write only on this board because I have a camera, so I can't do what I want. I will try to do my best, but I will have to erase too much, but let's do it. So, I consider a sub-sigma algebra of calligraphic A, and if I have x in L1 of omega AP, we define the conditional expectation of x given j in the following way. So it has to fulfill two conditions. Okay. First, the conditional expectation of x given j is j measurable. It's the first point to check. And then for all u j measurable unbounded, I need to check that the following equality hold. That is, the expectation of x given u has to be equal to the conditional expectation of x given j times u. So if you find a random variable z fulfilling these two conditions to be j measurable and fulfilling this one, by uniqueness you are sure that this is the conditional expectation of x given j. Okay. So it's something I have already seen during the previous session. Okay. And then if you want the conditional expectation given a random variable, you just have to take for j the smallest sigma algebra that make this random variable measurable, that I have called sigma of 1. Okay, so in the previous session I have stated proposition 0.4.3, where I am in the following situation. Okay, so I consider a random variable x fulfilling the following: sigma of x is independent of the sigma algebra j, y is j measurable, and I consider mapping phi such that, in fact, phi of x, y belongs to L1 of omega A. And in fact, in this situation, I can compute basically the conditional expectation of phi of xy given j. And we have a particular form for this one. It's proposition 0.4.3. Okay, I have finished with during the previous session. So I know by definition that it is something that is j measurable, but in this situation I can be more precise. This conditional expectation that is of course j measurable is in fact the function of y, where this function is known, this mapping is known, and equal to what? To the expectation of phi x small. I have this one. So be careful, as I have already stated, okay? Psi of y is not equal to this. Here you have a number, here you have a mapping, Okay, that is a mapping depending on the random variable capital Y. And I have explained to you why. Okay, because here, if you want, I integrate with respect to the same variable, while here I integrate only with respect to capital X. Okay, so be careful. I don't have this, and I have explained why during the previous section. Another remark. I said that psi defined this way is in fact measurable when I keep R with the Borel sigma algebra. Why I have this? Well, it's a consequence of something I have reminded during the previous session, that is the Fubini theorem. Since this one is in L1, okay, if I consider partial expectation, let's say, this one with respect to X, but I have an analogous result for the partial expectation with respect to capital Y, I am sure that I am measurable. So the argument is Fubini theorem. It's something I have reminded, okay, when I have spoken about the conditional density function. Okay, so it implies that if I have this one, phi of capital Y is J measurable by composition. Okay, well, let's do the proof. So, I have to check the two things. The first one is obvious here, because this one is J measurable. Okay, so if I want to prove that this one is this one, I already know that this one is measurable thanks to what I have reminded here. So the only thing it remains to prove is that this relation works taking psi of Y here. Okay? So I start with this one where U is J measurable and bounded. Okay? So it's the expectation of what is this? Phi of xy. I am interested in the conditional expectation of phi of xy, so I plug instead of x here phi of xy. For the moment, I use nothing for my hypothesis, okay? But what I have as an hypothesis, I have the fact that x is independent of j, and y is j measurable as u. U is also j measurable. So I know that x is independent of the pair y u. X is independent of the pair y u because, repeat, sigma of x is independent of j, y is j measurable, and u is j measurable. So x is independent of all the things that are j measurable as y and u. And what is the consequence of this one in terms of probabilities? It means that the distribution of the triple may be separated in two parts using independence. It's P of x product with P of the pair y u by independence. So when I write this expectation here, I can use what I have reminded here. In fact, this expectation is a double integral. Write it this way. Phi of x, y, u. Against what? Against the probability of the triple that I can decompose this way. Okay? And I can write it this way. I have this one. Okay? So it's a triple integral that I can write this way because of my hypothesis related to the independence between x and the pair y u. Okay. So what can I do here? In fact, I can introduce what I have introduced here. What is this one? It's exactly. So I can remove the u from the first integral because it's something that is independent of x. So I remove it from the integral. And so I obtain here, I continue here, integral of r squared u integral r of phi of x y dpx of x dp y u y u. I just remove the u from the first integral inside. But what is this mapping here? This mapping is exactly as I have defined as psi of y. Psi of y is the expectation of this one. That is just the integral of phi of xy with respect to the distribution of capital X. So you have here psi of y. And now it's finished. Why it's finished? Because I can come back to the form of an expectation. What I do, I compute the integral of u times psi of y with respect to the distribution of the pair yu. So this may be written as the expectation of capital U psi of y. And from the definition of the conditional expectation, I have written this quantity as the expectation of u times something that is J-measurable. By the definition of the conditional expectation, I deduce that the conditional expectation of phi of xy is just equal to psi of y. So it means in this particular situation, compute a conditional expectation is in fact not more complicated than to compute this expectation completely. Okay? And you will see that this little result will be used a lot, in particular in the chapter concerning the Brownian motion. Okay? So you have to know it, okay? And something that we are going to use several times in the chapter dealing with the Brownian motion, and even in the chapter dealing with the financial part. Okay? We will see later on that the prices of the financial products that will interest us will be conditional expectation. In order to compute these conditional expectations, sometimes it will be interesting to use these little results. Okay? Do you have some questions? Is it okay? It's just a little exercise concerning the definition of the conditional expectation. The idea was to recover this part of the definition just using my hypothesis. Yes?
Expectation of u outside of y the first
Speak louder, please. I don't understand. En français, si tu veux. Non, pas ça, c'est si de y, en vérité. D'accord, j'ai le début. If you want, I have checked that this one is equal to this one. That is the analogous of this part of the definition. So I can deduce from this, and from the fact that here I have something that is J-measurable, I can deduce that this part here is the conditional expectation of this one given J. Okay? This is exactly what I have written here. So try to do it again at home, okay? It's something that is a good exercise concerning the definition of the conditional expectation. Other questions? So if you have some question, maybe you can ask me. No? No? You want? Are you okay with proposition 0.4.3? So if you're okay, I will erase. And now the last little exercise we are going to do on conditional expectation is the link between conditional expectation and Gaussian vectors. Because in this situation, okay, we have nice results concerning conditional expectation and expectation. So if you are okay, I will erase everything. Okay, because to do the job, I won't have to come back to the definition of the conditional expectation, but just I will have to come back to its properties. So erase. Okay. So conditional expectation in Gaussian vectors. And typically, in the case of the Brownian motion, you will see that the Brownian motion will be what we call the Gaussian process. That is the extension of the notion of Gaussian vector, and it will be a result that will be able to apply in this framework. So, I am in the following situation. It's the proposition 0.4.4. So I consider the following vector, z x1 xn. I call it the first component z in order to underline it, in fact. Okay, and I suppose that this is a Gaussian vector. It's my hypothesis. In particular, since I have a Gaussian vector, I know that each coordinate is Gaussian. It's not equivalent, but it's a consequence of. In particular, all my random variables are in L2, so I will have to consider conditional expectation, because in the definition of conditional expectation, I need to be in L1 if I want to compute the conditional expectation. And here I will be in L2. And I say the following. There exists, write it this way, A, B1, Bn, such that the conditional expectation of z given the vector x1, xn, in fact, has a very particular form. So what I know, from what we have said previously, this conditional expectation, okay, is something that is measurable with respect to the sigma algebra generated by this vector. In other words, it means that this conditional expectation will be for sure a mapping depending on x1, x2, xn. Okay? So this is what I obtain if I just use the definition of what is a conditional expectation. In this very particular case, we will see that I have a function of x1, xn, but that is very, very particular. That is in fact something that is linear in x1, x2, xn. So there exists a, b1, bn such that this conditional expectation is just equal to a plus b1 x1 plus bn xn. Okay? So something that is not remarkable because we have an expression that is just linear in the x1, x2, xn. And it will come from the fact that I have a Gaussian vector. Okay, so here the idea is to say the following. I work here only with random variables that are in L2. And in L2, I have given to you in the previous session, in fact, an interpretation of the conditional expectation in terms of projections. Okay? In terms of orthogonal projections. So it's exactly what we are going to do. We are going to consider pi, the orthogonal projection of z, of the orthogonal projection on what? On the vector space generated by 1, x1, and xn. Vect of 1, x1, xn, okay, is the classical notation for the vector space generated by this n plus 1 element. And what is this vector space? It's just the set of the linear combination of these elements. Okay? So if I consider pi the orthogonal projection on this vector space, what I have, by definition of the orthogonal projection, okay, I know that z minus p of z. Okay, so if you want, I can do a little picture here. You have your vector space here, vector some 1. You have z that is here, and you do the orthogonal projection. By definition of the orthogonal projection, it means that the vector, this one here, this vector, is orthogonal to all these elements here. So, is orthogonal to 1, to x1, until xn. I am in L2 here. So what I call orthogonality is related to the scalar product in L2. That is the expectation of the product of the random variables. So what is the meaning of this one? It means that the expectation of z minus pi of z time 1 is equal to 0. It's the first orthogonality relation. And I have also expectation of z minus p of z x1 is equal to 0 until the expectation of z minus pi of z xn is equal to 0. Okay? So maybe let's give it a name here. Let's call it y. So this one means that the expectation of y is 0, the first line. And since the expectation of y is 0, here, in fact, I have covariances condition, because the expectation of one of them is 0. So here I can say that the covariance between y and x1 is equal to 0. The covariance between y and xn is equal to 0. Okay. But we have seen together that in the case of a Gaussian vector, I have particular relations between independence and covariance equal to 0. Relations that are not true in general, but that become okay in the case of Gaussian vectors. So what I have here? So I have these conditions, okay? And I can remark also that y, x1, xn is a Gaussian vector. Why I have this? My hypothesis is this one. Why I have the same hypothesis if I replace z by y? Y being this one. No. Yeah, no. It depends on what you have in mind. So if you have in mind that the orthogonal projection, by definition, is an element here, it means that pi of z is in fact a linear combination of such term here. This vector being Gaussian, if I subtract to z a linear combination of the previous term here, or an affine combination of this term, I am still a Gaussian vector. That's what you had in mind? Okay. So this one is a Gaussian vector, because pi of z belongs to vex of 1 equal x. So if you add to a Gaussian vector, okay, linear combination of the components, it doesn't change its Gaussian nature. So I have a Gaussian vector, and I have all these covariance relations. Covariance between y and x1 is equal to 0. Covariance between y and xn equal to 0. But we have proved together during the previous session that, or maybe during the first session, that if I have a Gaussian vector, covariance implies independence. So I can deduce from the fact that I have a Gaussian vector here and from this covariance equal to 0 that y is independent of x1 until y independent of xn. And the result we have also seen in the first session is that when I have a Gaussian vector, to prove that the first coordinate is independent of the last one considered as a vector, it is sufficient to prove the independence coordinate by coordinate. It's a result we have seen, so maybe it has a name, something like this. It was the proposition, the corollary (0.3.1), saying that when you have a Gaussian vector this way, if you have the independence component by component, in fact, you can say that y is independent then x1 xn, the whole vector, in fact, by a result we have proved together in the first session. And now it's almost finished, let's say. What I want to compute? I want to compute the conditional expectation of z given x1 xn. Okay, I will finish here. I want to compute the conditional expectation of z given x1 xn. But I can write z as using y. It is y plus pi of z given x1 xn. So by linearity of the conditional expectation, the conditional expectation of the sum is equal to the sum of the conditional expectation. What happened for the first term? The first term is independent of x1 xn. We know by the properties of the conditional expectation that if I have independence, the expectation is none other than the conditional expectation. So the conditional expectation of y given x1 xn by independence is equal to the expectation of y that is equal here to 0. For the second term, what is pi of z? Pi of z is an element of this vector space. So it means that it's a linear combination of these components. So I have something that is measurable with respect to x1, x2, xn. And so here I have simply plus pi of z. What I have proved? I have proved that the conditional expectation of z given x1, xn is equal to pi of z, simply the projection, the orthogonal projection. Okay? So if you want, in the previous session I have given to you the intuitive interpretation of the conditional expectation using orthogonal projection. In the case of Gaussian vector, here we prove that it works, in fact. Okay? And what is pi of z? The pi of z is an element of the space on which I project. So it's an element of this vector space, and so it's a linear combination of this element. That's why I have this one. It's a linear combination of this one that gives me exactly the form I want. Okay? So I prove here that in fact in this situation the conditional expectation is just the orthogonal projection on this space here. That's why I recover this result. And the main argument is that when I am in the case of Gaussian vector, I have deep links between independence and covariance equal to 0. Okay, so if I am not in my framework, I can't use this corollary that allow me to conclude. Okay? So I know in Greek generality that this kind of conditional expectation is a function of x1, xn. In the case of a Gaussian vector, I know this mapping. This mapping is just this one, something that is linear in my random variables x1, x2, xn. Okay? And I repeat that for this proposition and the previous one, okay, they will be used in the chapter 1 and also in the final chapters concerning finance. Because at the end, okay, the prices we are going to compute in this course may be seen as conditional expectation. We have to be able to compute them explicitly. The two previous results will help us to do. Okay? It will be a few weeks, but I will use this part of the reminder. Okay? So it closes the part concerning conditional expectation. I don't need more for the moment, okay? And we are going to deal with notions about stochastic processes. Okay? And before to start this new part, okay, just one word concerning why we'll be interested by stochastic processes. When we do finance, okay, so for example, you want to model the evolution of the price of an asset, okay, you have two things. The fact that the price of this asset in the future is unknown, if I am at time t equal to 0. So if I want to model it, okay, an interesting way is to use the notion of random variable. Something, okay, that depends on randomness. It's the first point. Second point, okay, since I will want to work with prices, what I know is that prices evolve a long time. Okay, so I will have random variables evolving a long time. But typically, the notion of stochastic process, that will be, as you will see in 1 minute, just a family of random variable indexed by something that we can think like the time, okay, will be exactly the notion in order to try to model the evolution of a financial asset, okay, a long time. That's why we are going to introduce. So it means that it's a second level with respect to the notion of random variable. Okay, if I am a random variable, I depend on W belonging to omega. I add a variable that is for the time. Okay, and we have to handle this notion. So we will speak about the measurability of these stochastic processes, the way to compare them, and so on. And today we are going to spend time on this. So you will see that it will be a little bit technical. Maybe the course that is the most technical, okay, in the 12 sessions we have, or 16 sessions we have together. But in fact, if you are okay with the notion of measurability for random variable, it won't be that complicated. If you are not, it will be the way to spend time on these notions. Okay? So may I erase my board? Yeah, question before? Ah oui, oui. Fort. Non? Oui, on a tort. C'est une fonction de L2 dans les deux.
Si c'est la collection orthogonale sur un
ouais. Ouais, c'est juste que tu in fact, when you do an orthogonal projection, you project on a space. Whatever this space is. It just needs to be a subspace, in fact a closed subspace in a Hilbert space. It's exactly my situation. So here I have just elements that are my random variable, and I agree with you that since I work with elements that are random variables in L2, pi of z will be a random variable, yes. That is just an element of L2. Okay, consider as a space. P, pi, is just a mapping. Pi is a mapping from L2 of omega A P into vect of 1, x1, xn. Pi is a mapping. For any z, I associate to any z its projection. Okay. P of z is an element of vec, and pi is a mapping. Okay. C'est un ensemble. It's a space of random variable, not random. You have as elements of this space random variable, but elements. In a space you can have inside anything you want. You may have mappings, you may have points, you may have numbers, you may have vectors. Here, I just work, okay? But I am agree with you that in fine, what I will obtain for P of someone will be a random variable. It depends on W in omega, okay? But this space is not random, okay? It's just the space of the linear combination of all these terms. We obtain a vector space of finite dimension that is for sure less than n plus 1. I don't know exactly what is the dimension because I don't know if there are relations between these variables, but it's a vector space, okay, of finite dimension. Other questions? No? Erase? So I erase everything and we start the new part. So, as you have remarked, okay, I see in the chapter 0 a lot of different things, okay, Gaussian vectors, conditional expectation, now we are going to pass to stochastic processes, and then we are going to pass to martingale. But the idea, okay, is that a priori, in a wonderful world, okay, all this notion should be okay for you. But as I know that we are not in a perfect world, okay, that's why I spend time at the beginning to be sure that everybody will be okay with the content, and you will see that from the chapter 1 to the end, after we are going to use a lot all these results, okay, that would be just the way to compute things that are related to finance. But I prefer to spend time on this because I think that for the final exam, for example, it will be these points that will be a problem for you, not the new things that we are going to see together, okay, but basic things concerning probabilities you have forgotten, okay, from previous years. That's why I have a huge chapter 0, and I don't start directly with the chapter 1. Okay. So stochastic processes. So stochastic processes that we are going to use in this course. Not, it should be, if it can be a course by itself, okay, but I will restrict myself to the one that will be used in this course. And typically, since we are going to work with the broad motion after all, okay, it will be continuous time stochastic processes. So let's see the definition. That is a very general one. Okay. So a stochastic process on the probability space omega AP that is indexed by T included in R, a subset of R, okay? Or in fact R plus, if I want to have the time in mind, is the family xt, T belonging to capital T, of real random variables. So it's something that is very large. Huh? Something that is very large. Just a family of random variables at this stage. Okay, nothing more complicated. The only thing that you know is that anytime you take an element in capital T, you have here a random variable with respect to this probability space. Okay, so I know that xt for fixed t is something from omega AP into R equipped with the Borel sigma algebra. Okay, and you have here a random variable that is for all b belonging to b of R, x t minus 1 of b will belongs to calligraphic A. It's the only thing I have. A family of random variables. Okay? No extra hypothesis. Okay. When you have two random variables, okay, in the course of probability, right, you have several ways to compare them. You can say that a random variable x and a random variable y are equal. If they are equal, let's say p almost surely. Okay, so the probability that they are equal is equal to 1. It's one way to compare two random variables with this notion of equality. You can also say that two random variables are equal if they have the same distribution. Something that is equivalent to say that they have the same distribution function or the same characteristic function. Okay? So you have several ways in order to compare, and you know that in the case of two random variables, if they are equal almost surely, of course they will be equal in distribution. Okay. Here, I want to introduce the analogous of these notions by taking into account the fact that I have a time dependence here. Okay. Intuitively, capital T will be, okay, something related to the time that evolves. So it's what we are going to do, okay, to try to compare, and we have some technical aspect to this comparison. Okay, so a stochastic process is just a family of random variables, and we are going to introduce three definitions and see, okay, what are the links between them. Okay. So definition 0.5.2. So two stochastic processes xt and yt are equidistributed if what? In fact, it's the extension of saying that if you have two random variables, they are equal in distribution, or if you have a random vector, two random vectors are equidistributive if they have the same distribution. Here, it will be the analogous, taking into account the time here. That is for the following. So if for all n belonging to m star, for all t1, tn belonging to t to the power n, so it means that I take n arbitrary instance in capital T for any n, okay, then x t1 x tn has to be equal in distribution. It means equal in distribution, means that the two vectors will have the same distribution with yt1, yt. So in other words, two stochastic processes will be equidistributed if and only if all the random vectors I can build from these two stochastic processes are equal in distribution. Okay? So this is the meaning of being equidistributed. So in particular, I have xt1 that is with the same distribution and yt1, xt2 with the same distribution and yt1, yt2, and so on for any n. Okay? In fact, it's what we call to have the same distribution for two stochastic processes. All the related random vectors have the same distribution. Okay? So it's the first definition we see. Second definition. Xt is a version of yt if for all t belonging to capital T, the probability that xt is equal to yt is equal to 1. T by t, they are equal almost surely. It's the definition of being a version of. Xt is a version of y if and only if for any fixed t, the probability to be equal is equal to 1. Which definition implies the other one? Is one definition imply the other one? In the case of random variables, you have the equality in distribution and the equality almost sure. And which one implies the other? Converse. It's stronger to be equal almost surely than to have the same distribution, because if you are equal almost surely, of course you have the same distribution function. Okay? So I have that this one implies this one, because if for fixed t I have this one, it means that these vectors are equal almost surely because I have a finite number of components. So to be a version of implies to be equidistributed. It's clear for everybody? It comes from the result that if you have two random variables equal p almost surely, they have the same distribution. The same for vector with a finite number of components. Okay? Last definition, and after we will see some examples. I have this one. We say that xt and yt are indistinguishable, indistinguishable, a little bit complicated to write and to pronounce, okay? Indistinguishable, indistinguishable if I have the following: the probability of the intersection over t of the events xt equal to yt, this is equal to 1. Xt and yt are indistinguishable if the probability of the intersection of xt equal to yt over small t belonging to capital T is equal to 1. Once again, are you able to compare these two definitions, for example? Is one imply the other or not? Point implique 4? No. So, the other. Why I have this? Because the intersection is the smallest. The intersection is included in all of them. If you have the probability of the intersection that is 1, of course the probability of each of them will be 1. Okay? I said that the last definition implies the previous one because, I repeat, the intersection is included in all these sets here. So if this one has a probability equal to 1, since this set is included in this one, of course the other one will be of proba 1. So I have this. So I have three definitions. I have these implications concerning the definition. Okay. And we are going to see deeper links between this definition, in particular between the two last ones. So just a little remark. So you have understood here that intersection being included in this one here, if the proba is 1 for the intersection, the proba of this one will be 1 for sure, because the intersection is included in each of them. Okay? So I have this. First question here. Do you have in mind a very simple condition on capital T in order to make the two last definitions equal? So a simple condition on capital T in order to make the two last definitions equal. So a priori, capital T is an arbitrary subset of R plus. Okay? Capital T is an arbitrary subset of R plus. Do you have a basic condition on capital T in order to make definition 054 and 053 equivalent? Yeah, it works. So it's not very large condition, but it works. In fact, if I have in capital T only one time, okay, I take a singleton for capital T, of course it works. Okay, so write it. If I take for capital T just T0, well, of course it works because the intersection is an intersection over one set simply. So I have the coincidence between the two. So when capital T is a singleton, it works. Other examples? If I try to be a little bit more than a singleton, we have 2 points, 2 instants inside. It works or not? Yeah. If you remind, what we know from probability theory is the following. I have two statements that are complementary together. First statement, if you have a sequence, something that is indexed by the natural number. If I have a sequence of sets with probability 0, the probability of the union has also a probability equal to 0. You remind this? So the complementary statement is if you have a sequence of sets with probability 1, the probability of the intersection is also 1. And why it works? It works because you know that in the definition itself of a probability, you have sequences. So you have something, the definition of a proba is related to the fact to be countable. We work with countable sequences, okay, by sequences that are just countable families. So I repeat, if I have a countable sequence of sets with proba 1, the intersection has also a proba equal to 1. So-called result in probability theory. So it means that if I take capital T to be countable, then both definitions coincide. If I take capital T countable, both definitions coincide. And my argument is, I repeat the last time, if I have a sequence of events with proba 1, the probability of the intersection is 1. It works for sequences. So families that are countable. If you remove this condition, it doesn't work. Okay? So typically, I don't know what you have done in the second semester the previous year, but if you have worked, for example, with discrete time Martin walls or something like this, okay, or discrete Markov chains, it wasn't necessary to introduce these two definitions because in fact they are the same. So you can say this one, for example, to be equal time by time, okay, and without entering into this kind of detail, because in this situation, all the things are equivalent. But unfortunately, in this course, we won't be in this situation, because we are going to work in continuous time. Okay, we are going to do finance in continuous time, based on the ground motion. Okay, so there is a case where it works, they are equivalent, but it won't be our case. So is it clear for everybody this? Countable implies equivalence between the two, because working with sequence is okay with working with probabilities. Okay, next question. If it works in this situation here, is it possible to impose some regularity condition on my stochastic processes in order, in some sense, to come back to this case? I explain myself. Here, capital T is included in R plus, so in general, capital T won't be tables. But we have cases in R, okay, where we have so-called countable sets. For example, the rational numbers that are at the same time countable and dense in R, meaning that any real number may be written as the limit of a sequence of rational numbers. And do you remind in analysis, okay, some conditions, some criteria that allow you to pass to or from one property defined on the rational, let's say, to a property that will be okay for all the real numbers. So, or we pass from Q to R in general when we do analysis. There is one word that allows to do this. So to be more precise, if I have two mappings that are equal on the rationals, do you have a criteria in order to ensure that they are equal everywhere? Yeah? Continuity. Okay? If you have a mapping that is continuous, to be equal on a subset of R that is dense or to be equal everywhere is exactly the same thing. Okay? It's exactly what we are going to use here. That is, that if I impose some conditions on the regularity of the trajectories of my stochastic processes, then the definition will coincide. Okay? But first, I write what is to be continuous or to fulfill some regularity for a stochastic process, and then we are going to use this in order to prove that in some situations that are good situations, that is when the trajectories of my stochastic processes will be regular. In fact, to be indistinguishable or to be a version of is exactly the same thing. So, definition 0.5.5. Okay. The stochastic process xt is continuous if we have the following. The probability of the set of the W belonging to omega such that the mapping T gives xt of W from capital T into R is continuous. I want this probability to be equal to 1. This is the meaning of being continuous for a stochastic process. This kind of mappings here is what we call trajectories. You fix the W and you make the time move, and in general, okay, it is what you observe if you observe the behavior of a financial asset. You observe one particular trajectory of this asset when W is fixed and when the time is moving. So in other words, a stochastic process is continuous if its trajectories are continuous as function mapping from capital T into R, and here the continuity is the classical one because T, capital T, is a subset of the real number. Questions? So the probability of the W belonging to omega such that T gives xt of W is continuous. Okay? Is 1. This is the meaning of being continuous for a stochastic process, that is, my trajectories are continuous with proba 1. The set of my trajectories that are continuous has a probability equal to 1. And of course, question? Trajectories. Okay, it's what we call the trajectory here. If I fix a W and make the time move, okay, what I obtain, it's the trajectory, it's a trajectory of my stochastic process. I fix the randomness parameter W, I make T moves, okay, and I obtain a trajectory. Of course, in the following of this course, I can replace continuous by anything I want. That is, we say that a stochastic process is differentiable if P almost surely its trajectories are differentiable. So if the set of the trajectory that are differentiable is equal to 1, I can replace continuous by of class C infinity if the trajectories are of class C infinity with proba 1 and so on. Monotonic. A stochastic process is monotonic if the set of the trajectories that are monotonic has a probability equal to 1. Okay? So for a stochastic process, we will say that this stochastic process fulfills the particular property is if the probability of the set of the trajectories that fulfill this property is equal to 1. Okay? So it is for almost all trajectories. Okay? So I have this one. So is this definition clear of continuity? Everybody? And you can replace what I have circled here, you can replace it by any property you have in mind, okay? To be right continuous, to be left continuous, to have left limit, and so on, okay? To be differentiable, to be monotonic. Okay. And now what we are going to see, as I have said that two continuous mapping on the rationals coincide on all R, we are going to use this idea, proving now, as a little exercise, that if you have two stochastic processes that are continuous, these two definitions coincide. So it's an element of a remark, yes. An exercise. Exercise 0.5.1. The first statement. If xt and yt are continuous, C0 I rewrite from now on, okay, for continuous. Then, so continuous in the sense of my definition 0.5.5, then by the definition 0.5.3 is equivalent to the definition 0.5.4 in this situation. That is, to be a version of is equivalent to be indistinguishable. So we have already seen that this one is always true. So the only one I have to prove is this one. That this one implies this one in the case where my stochastic processes will be continuous. And I repeat, so it's not that complicated. The only thing you have to think about is that when you have continuous mappings, they coincide everywhere when they coincide on rational numbers. Okay? So my trajectories pure martially will be equal if they are equal on rational numbers. Okay. So let's do the proof of this one. So I have two stochastic processes that are continuous, meaning this. Okay? So, if I denote by capital A the set of the W such that T gives xt of W is continuous, I know from my definition that P of A is equal to 1. Okay, by definition 0.5.5. If I define by B the set of the W such that T gives xt of W is continuous, not x but y here. But I know also that P of B is equal to 1. And I know, so I prove, okay, the side, I prove this side here, okay? Because the other one is always true. So I have this one, and I know that for all t belonging to capital T, I have the probability that xt is equal to yt, that is equal to 1. Okay? And my job is to prove that the probability of the intersection of all these events here is equal to 1. Okay? I want to prove that this definition implies this one. So these are my hypotheses, and I want to prove this one to prove that this one implies this one. Okay? So why I have this? T, ça, oui, ça peut être c'est quelconque en fait. On va voir. un autre coup, on prendra un sous-intervalle de R, ça marche. Est-ce que si T est méchant, on va voir. Ça colle. Ok. Alors, si la preuve elle passe. Okay. So the idea is just to say what I have said previously. When I am continuous, if I coincide on the rational, I coincide everywhere. So I can write the following using my notations here. I can say that A intersected with B intersected with the intersection, I will comment after. This one is included in this one. So why I say this? So it's exactly what I have said here. So what are the two first parts of my intersection here? I focus my set on the set where they are continuous. Then I said that here they are continuous, here they coincide not on whole capital T, but on whole capital T intersected with the rational numbers. Okay? And I said that if I am in this situation, they coincide everywhere. The argument is that the trajectories are continuous and Q is dense in capital T, in R. So maybe you are right, in fact. If I want to be totally correct with this proof here, if you come back to my definition of a stochastic process, I have said that capital T is included in R plus. So if I want to be totally clear, and it will be exactly what we are going to do after, because we are going to take for capital T a closed interval or the whole R plus, okay? It's better to take a subinterval of R. An interval we take, okay? Why it may have a problem? Because, okay, if I want to use my density argument here, I have to be sure that, I can say the following. I can also say that T intersected with Q, no, if I want to be correct, take for capital T a subinterval of R in such a way that you are sure that this one is dense in this one, in fact. So if you come back to my definition, okay, and typically because it's exactly what we are going to do after, what is what? The definition of this one. The definition 0.5.1, okay? Instead of take, so in the definition you can take capital T any subset of R plus, okay? And you can take for capital T, in fact, two particular cases, okay? Capital T is countable, okay? Or capital T is a subinterval of R plus, and in this way it works, okay? And what is my problem is that if I want to use my argument here, what I have written is okay. Whatever, okay. So here, it's the set where the trajectories are continuous. I suppose them equal on the set capital T intersected with the rationals, okay. If I want to deduce that they coincide everywhere, in fact, T intersected with capital and with Q has to be dense in capital T, meaning that any element in T may be approximated by a sequence of elements in T intersecting with Q. Okay. So this work, if I take, okay, a situation where T intersected with Q is dense in capital T. And why it's finished if I am in this situation? So keep in mind what I have to do. My hypothesis is this one, P of A 1, P of B 1, P of this one 1. I want to prove that the probability of the intersection is 1. Okay? I prove that this intersection is included in this one. If I want to prove that this one is 1 with proba 1, I can prove that this one is with proba 1. But it's the case here, because what I have done, what is the big change between this one and this one? Here, I have a countable number of terms in my intersection, while here, a priori, capital T is not countable. Using continuity, allow me to come back to the countable case. So, this probability is 1 from the fact that I have my hypothesis and from the fact that in my intersection here, I have a countable number of sets. So, the proba of this intersection is 1, and so the proba of this one is equal to 1. That was exactly what I want to prove. Okay? So in the case where my trajectories are continuous, in this situation, to be indistinguishable or to be a version of will be the same. Something that is that flexible because a priori it's easier to prove this for you instead of proving this. Because you have to check what is this intersection, while here you just have to work with these events here, okay? And you will see that in the financial part we are going to work with continuous stochastic processes. Meaning that if I want to prove that they are indistinguishable, it is sufficient to prove that I have this one. Something that is easier and easier to prove. Okay? Question? Is it clear? No? Ça va? Un peu brutal. Mais c'est la partie la plus brutale du cours. Jusqu'à février. No. I think that from the beginning of September until mid of October, yes, it's the hardest part of the course. Okay? Because, okay, I remind a lot of things that has to be reminder, but I know that for most of you it's not the case, or maybe you have seen this a long time ago. You have to remind everything, okay? But you will see, if you spend time working in a good way on this chapter 0, after, okay, it will be really smooth, in fact. The idea will be just to use, okay, to pick in the chapter 0 in order to do proof that will be, let's say, less abstract, okay? So if I come back to this proof, are you okay? At the very least, intuitively, I want to prove that I can pass to this one to this one. I know that it's true in the countable case, because when I have a sequence of set with proba 1, the intersection has proba 1. I want to come back to this case, okay, in a more general situation than capital T countable. If I impose this regularity, that is the trajectories of my stochastic process are continuous, by what I have said here, in fact, I can come back to the countable case, because to coincide everywhere or to coincide in the countable case in this situation is the same when I have the continuity of the trajectory. Okay? So here I have a countable number of sets in my intersection, if each of them being of proba 1. So the probability of this one is 1, implying that the probability of this one is equal to 1, and so I have proved that they are indistinguishable. And I repeat what I have said. In this course, I will work mainly with stochastic processes that are continuous. So in order to prove this, it is sufficient to prove this in general. In 99% of the case, it will be this. Okay? But you will see that this notion of equality is in fact the good one between stochastic processes. Of course, it is maybe the most abstract one, okay, but the one that is the most flexible for what we want to do. Questions? Yeah. By density. So two things. T intersected with Q is dense, and this one, you have something that is countable, because Q is countable. Okay? And so you come back to this. No. You have a question? In French, if you want. Or in English. Okay. Is this inclusion okay for everybody? I have the answer, no, but I am sure that it's not. Are you okay with this one? Yes? So the argument is the following one. Huh? When you have the general argument, when you have two mappings from R into R that are continuous, when they coincide on Q, they coincide everywhere using the density. Okay? If you're okay with this one, it's exactly my argument here. Because I consider the set where they are continuous. So they are continuous on this set. So I know that if W belongs to this one and W belongs to this one, both trajectories are continuous. So if the trajectories coincide on the intersection between Q and T, it will coincide, and they will coincide everywhere. Okay? Using a sequential argument, and you take an element here. Since T intersected with Q is dense, you can find a sequence and you can pass to the limit using the continuity. Okay? Think about this. But before to do the little break, just a counterexample of the other implication. Okay? Because I have said it works if they are continuous, but it doesn't work every time. Just to show you one example where I don't have the equivalence between these two things. Okay? So I keep the definition on the board and I will erase. And of course, if I want a counterexample, it won't be an example where the process will be continuous, because when they are continuous, it works. Okay? So it's not this situation. So it's the continuation of this exercise with an example where this one doesn't imply this one, implying, from what I have done previously, that the stochastic processes we are going to consider are not continuous. Okay, so I erase it here in order to keep the definition on the board. And then we will do the break, and after the break we are going to speak about measurability of stochastic process. Okay. So I take a particular counterexample of this implication to prove that it is not true in general. Okay? So for omega A P, I take the following. I take the interval 0, 1, the Borel sigma algebra on the interval 0, 1, and I take dx, that is just the Lebesgue measure here on the interval 0. Whatever. The dx, you know, okay? That is the Lebesgue measure on the interval 0. That is the probability in this. Okay. So I consider A, that is a strictly positive number that will be fixed. Okay? And I define xt. So, excuse me, so I am in this exercise here. I have a first question, and here it's a second question to prove that this implication doesn't hold in general. Okay? So don't hesitate to ask questions, okay? Typically, I know that my board is small, so I have to erase. It's not that comfortable, but I don't have the choice if I want to record. Okay? So I define xt this way. Xt of w is equal to w plus a times t, okay, for t belonging to r plus, and w belonging to 0, 1. So it's a stochastic process indexed by R plus, the word R plus here, omega is the interval 0, 1. And here, if I want to plot the trajectories, I will apply, okay, I will obtain something like this. You have W here, and you will have something like this. You have the trajectories of xt here. That has this kind of lines on R plus. Okay? For yt, I define it in the following way. Yt is equal to what? It's equal to W, so yt, excuse me, of W is equal to W plus AT if t is different from W and 0 otherwise. Yt is equal to the same thing when t is different from W and 0 otherwise. So it means that here I have my W. If I want to represent this one, okay, but it will be more or less the same except for this one where I will have a 0 here. Okay, so I have only one color, but you have the trajectory here of x, and if I find my other color, here the trajectory of x, and for y you have the same thing except for this point here where for t equal to W I am equal to 0. So they are not that far, the trajectories, huh? They are the same except for one point or one time, that is for t equal to W. Okay, so what I want to prove with these two particular cases, I want to prove that in fact xt is a version of yt, but that xt and yt are not indistinguishable. So I want to prove that the definition 0.5.3 holds, but not definition 0.5.4. So what is the set xt equal to yt? So when xt of W is equal to yt of W, when W is not equal to t. Okay? So this set is all the W, yes, except t from my definition. Xt and yt coincide, okay? Now keep in mind that this set is just the set of the W belonging to omega, such that xt of W is equal to yt of W. And when I come back to my definition, they will be equal if I am in the situation, that is when W is different from t. So W belongs to the interval 0, 1 minus t. So of course, if I ask you to compute this probability, since the underlying probability is the Lebesgue measure, you know that the Lebesgue measure of one singleton is equal to 0. So the Lebesgue measure of this one is equal to 1, the size of my interval, 1. Okay? So xt is a version of yt. Because I repeat, if you compute the probability in this situation of 0, 1 minus t, it is 1. Okay? The Lebesgue measure of one point is always equal to 0. Okay? The interval or the interval minus, in fact, a countable number of points have the same probability. Now, I am interested with this one. Okay? The intersection t belonging to capital T of xt equal to yt. So can you tell me what is this set? Can you tell me what is this set? But this one for fixed t, but you do the intersection over all the t. It means that you subtract all the t belonging to R plus at the end, how many elements? This set is just the interval 0, 1 minus t. And I do the intersection of all this type of. Il reste que les éléments de. Ouais. Alors T, c'est, excuse-moi, c'est R plus ici. Hein. T, T, T. Ok. C'est plus grand monde. Not zero, huh? Zero in terms of space, empty set. Empty set because, okay, what are this one? This one, okay, are just interval 0, 1 minus t. If you do the intersection of all of them for t belonging to R plus, you subtract of all the points of the interval 0, 1. So you have here an example where the probability of each of them is 1. So xt is a version of y, but the probability of the intersection is not 1. Even it's 0. Okay? So it was just an example in order to show you that definition 0.4.3 doesn't imply, in general, definition 0.5.4. It works in the case where the stochastic processes are continuous, and even in the case where we have a single point of discontinuity, you see that it doesn't work. But fortunately, later on we will work on continuous processes. So you have here on the board an example where xt is a version of yt, and xt and yt are not indistinguishable. Okay? Break? So we have seen in particular these ones that are some notion in order to compare stochastic processes. And now we are going to start with the notion of measurability. Okay? So I erase everything and do some comments before to give you the definition. So if you are okay with measurability, you will be okay with this definition, but I prefer to remind. So, if you have a single random variable, I will repeat something that I have already said. Be measurable or being a random variable, that is the same. Means that for any element in the Borel sigma algebra, if I take its preimage, it has to be in calligraphic A. This is the definition of measurability. Well, this one, I remind you that it is the set of the W belonging to omega such that x of W belongs to B. Okay? So I want the analogous of this definition for stochastic processes as defined previously. And typically here I will focus on this case for T belonging to R plus. Okay, I will take capital T equal to R plus in the definition. Because I need to have a Borel sigma algebra on the set of indexes, okay, so I will take R plus, okay, but it will also cope with the case where capital T is a subinterval of R plus. Okay, so from my definition of a stochastic process, I have what? I have a family of random variables here indexed by R plus. It's one way to see. But it's not the only way to see a stochastic process. You can also see it as a random variable, but depending on two variables, T and W. So it means that my stochastic process can also be defined the following way. From R plus time omega that associate to any time and any W xt of W. So I have something that is from R plus time omega into R. It is this way. So you have just, okay, something that I can call capital X. That is another way to write my stochastic process and to see it just as a random variable depending on two variables, the random parameter that is classically W in omega and the time parameter. And of course, I can equip each set with a sigma algebra. Okay? So instead of writing only the set of parameters, I know that I have on R the Borel sigma algebra. I have on R plus the Borel sigma algebra on R plus. And on omega, I have my initial sigma algebra that is calligraphic A. So just to say that to consider a family of random variable indexed by R plus is equivalent to consider the mapping that associate to any time t and any w in omega xt of w. Okay? And in fact, the definition of measurability will be the same as this one, but with this new situation. Okay? So it's exactly what we are going to write in the definition 0.6.5. Xt t belonging to R plus is measurable if what I have written here, if the mapping that associates to tw xt w from R plus b of R plus time omega a with values in R b of R is measurable. Meaning that for any Borelian, the preimage has to be an element of the product of the sigma algebra. So it is possible to write this in another way. Equivalently, for all t belonging to R plus, or all t0, let's say, for all b belonging to b of R, then the following set this one has to belong to b of 0 capital T time calligraphic. So this is the definition of the measurability of a stochastic process. And a priori, if you are really okay with this definition of measurability, it's the same. Just having in mind the fact that I don't have a single variable here, I have two variables. This is just this one, okay, the pre-image by the mapping capital X of my Borelian, okay, if I restrict the time to be 0 capital. So this is the definition of measurability that we are going to work with, okay? I remind you that this definition, that is the product of two sigma algebra. Okay? Keep in mind that the product of the two sigma algebra is not the set of the pair where the first is an element of this one and the second is an element of this one. It's a little bit more complicated. In fact, it's the smallest sigma algebra that contains the pair where the first element is an element here and the second element is an element here. The smallest sigma algebra, let's say, generated by the rectangles where the first is an element of the Borelian sigma algebra in 0 capital T and the second is an element of calligraphic A. And in general, to prove that a property is true for all the elements of this form here, it is sufficient to prove that it is okay for the rectangles that are, I repeat, the product of elements in here and here. Okay. So I have this definition of measurability. So just a remark concerning this one. To show you, okay, in which way it will help us, okay, when we are going to work in finance a little bit later on. I say the following. If xt is measurable in the sense of the previous definition, and if f, okay, belongs to the continuous mapping that are bounded from R into R. This notation means I am continuous and bounded. Okay? Then I said the following. Then, if I define yt as the integral between 0 and t of f of xu du, okay, the partial integral related to f of xu, I said that then yt defined this way is a stochastic process. So what is the meaning of this? Keep in mind that being a stochastic process just means, so yt is a stochastic process, just means that for all t belonging to R plus, yt is a random variable. Okay? It is the meaning of a stochastic process. A stochastic process is just a family of random variables indexed by R plus. So I said that if I start from a stochastic process that is measurable in the sense of this definition, and if I consider this partial integral here, the integral depending on the upper bound, okay, then I define this way, under my condition of measurability, something that is a stochastic process, that is for any t, yt is a random variable, that is measurable. Okay? So why I have this? But in fact, it will be once again a consequence of both the definition of measurability, of course, and of the Fubini theorem. So let's define the following. So I define the following mapping. SW that associate to any S and any W the following: integral between 0 and t of S, f of xs of W. I define this one, okay? So this one is defined from R plus time omega with values in R. Okay? What can you say about this mapping here? What can you say about this mapping? So for fixed W, if you want, but it's not what I had in mind. So they are equal to this one if I am in the set of the indicator function and 0 otherwise. But I have a little bit more with my hypothesis here. You know that with measurable mappings you can do what you want. You can do sums, you can multiply, you can do compositions, and so on. Okay? So in my expression here, it involves what? It involves something inside that is measurable. I have f that is regular in the sense that is continuous, so measurable. And I multiply by the indicator function of an interval, so something that is measurable also. So by composition and multiplication, I have inside only things that are measurable. From this definition, the fact that f is regular, continuous, and the fact that I multiply by the indicator function of an interval, something that is measurable with respect to the Borel sigma algebra on R plus, because 0t is an interval. So I have this one that is measurable. I repeat, the argument is that here, measurable by definition. I do the composition by something that is continuous. I stay measurable and I multiply by the indicator function of something that is regular. I am still measurable. So I have the measurability of this mapping. I know also that f is bounded. So I have something that is measurable and bounded. Measurable and bounded. So I am typically under the hypothesis of the Fubini theorem, because I have something in L1, because I have something that is measurable and bounded, so in L1. And the Fubini theorem tells me that if I consider the partial expectations or the partial integral here, then what I obtain is a random variable, something that is measurable. So typically here, if I fix W and do the integral with respect to the time, what I obtain? The integral between 0 and plus infinity of integral between 0 and t of s f of xs w ds. This is equal to what? Exactly what I am interested in. So this one, W if this one is measurable by Fubini theorem, and what is this? This integral, I do the integral, so my bound is in fact between 0 and t of f of xs w ds. Exactly what I want. So when you consider a measurable stochastic process in the sense of this definition, if I consider this type of partial integral, I obtain, as a byproduct, a stochastic process once again. So partial integrals of adapted stochastic process, okay, stay a stochastic process. And you will see that in the financial models, okay, these kind of integrals will be used, okay, to describe the dynamic of a financial asset. So for the moment we are very far from this, but just remark that if I impose a good measurability condition on this one is a random variable. Okay, so I can consider the probability that it is equal to someone, I can consider its distribution, something like this, okay? So yt for fixed t is a random variable that is measurable, and it's a consequence of Fubini, because this one is measurable by composition and multiplication. When I consider the partial integral with respect to the first variable, I know that what I obtain at the end is something that is measurable by Fubini theorem, and so this one is. So this kind of partial integral is measurable by the fact that I have support that my process is measurable. Okay? So it's my first point. Second point. When I see this definition, okay, I can say that it's not that intuitive to understand, okay, for sure. It's not very far from what happened for a single random variable, but since I have two variables, okay, I have all these pre-images to consider, so it's not that easy to handle. To prove that something is measurable, I have to check that all these terms that may be complicated belongs to this sigma algebra, and sometimes it may be tricky to do this. But fortunately, what we are going to prove now is that if you work with a stochastic process that is continuous, then it is measurable. Continuity implies measurability for a stochastic process. Okay? And since, for example, the grand motion we are going to work with will be continuous, typically it will be measurable. Okay? And if you have, instead of x here, the grand motion, you will have random variables that may be defined this way. Okay? So what we are going to prove, I repeat, is to prove that a stochastic process that is continuous is measurable in the sense of this definition. Okay? So it's what we are going to prove now. The way we are going to prove is the following. From probability theory, you know that when you have a sequence of measurable random variable that is convergent P almost surely, you know that the limit is a random variable. Okay? To be a random variable or to be measurable is something that is preserved passing to the limit. So what we are going to do is to prove that when we have a stochastic process that is continuous, it will be possible to approximate it in an efficient way. Okay? In the sense that my approximation will converge when n goes to plus infinity, almost surely. And it will be not that complicated to prove that all the elements of my approximation are measurable in this sense. And so I will conclude that my limit, that is my initial stochastic process, is measurable. And the fact that I am able to approximate will be the consequence of the continuity of my process, that is the consequence of the continuity of its trajectory with proba 1. Okay? So it's what we are going to do. So I will erase everything. I will just remind on the corner of the board what is the definition of being measurable. That is this condition here. And we are going to see what happens. Do you have questions before I erase? Question? No? So I write it here. So measurability for a stochastic process. For all t belonging to R plus, for all b belonging to the Borel sigma algebra, I want to prove that the set of the t w belonging to 0 capital T times omega such that xt of w belongs to b. I want that this set belongs to the Borel sigma algebra of 0 capital T times calligraphy. It will be my job to prove measurability. What we are going to prove now is the following. It's what I have called exercise 0.5.2. That is just xt continuous in the sense of the definition I have introduced before the break implies xt measurable. And I repeat that a priori it's easier to prove that the trajectories are continuous with proba 1 than to prove this condition that seems to be a little bit complicated. Okay? So let's do the job. And the idea, I repeat, will be to prove that using the continuity we are going to be able to approximate our process in an interesting way. Okay, so what I want to prove is this one, okay, for any capital T. So I will fix the capital T here. And I have my stochastic process. So I know that the trajectories are continuous. So if I represent a trajectory, here I might have something like this, let's say, why not? Just something that is continuous. What we are going to do, so here what I have represented, okay, it's xt of w, and I know that for almost sure w, for a set of w with probability 1, I have the continuity of the trajectories here. Okay, you have the time here, you represent xt of w. Okay, so how to approximate my stochastic process? But basically, in fact, it's exactly what you do in the case of the construction of the Riemann integral, for example. We are going to approximate our stochastic process by something that is piecewise constant. So we are going to consider a discretization of my 0 capital T and consider something that is stepwise constant on this. So for example, okay, we are going to take, let's say, T over n, T over n, until capital N. So I consider a subdivision of step size capital T over n. Okay? And the way I approximate is the following. So on the interval zero T over n, we are going to approximate our trajectory by this one. That is here just the value at time 0 of the volume. Why not? Okay? So it's exactly what you do when you build the Riemann integral, okay, from Riemann sum. So I do this. For the other interval here, for this one, on t over n to t over n excluded, I will approximate my mapping by something like this. Where here I have x t over n of w. And I do this until the end. So here, between n minus 1 t over n, so I do this one. And at the end, I have a single point in the last, okay, and I take x capital T.
Sorry?
Yeah.
I remember that shouldn't approximations be always on some the same side of the curve, like always below or always above?
No. Yeah, I know what you mean, okay? I just say that here, so when you have in mind that in the construction of Riemann integral, you consider the mapping that are stepwise constant and below or greater than, and then you build integral for both type of mapping and prove that at the limit give rise to a single thing that is just the Riemann integral. Here it's not what I do. Okay, I just say that I approximate by stepwise constant, and the way I do is that on every subinterval I consider the value of the process on the left part of the interval. So if I want to write it properly, not with just a mapping, okay? So what I have defined in orange here, it's a stochastic process. So for t belonging to 0 capital T, I can define x n t of w that is equal to what? So first of all, at the end, it is equal to x capital T. They coincide at the end. So I can put when small t is equal to capital T, I am equal to x capital T of w. Okay, it's the last point of my approximation. And before, I have what? I have a sum of what? Of the indicator function of each interval of this type here. That is, indicator function of something of the form kt over n, k plus 1 t over n, small t. So I erase this one and I write it below. And I approximate on this subinterval my process by what? By the value on the left part of the interval. So I have here x, k, t over n, w. So it's exactly what I have represented in orange in my picture here. The approximation I have plotted here, that is something that is piecewise constant, is represented by this one. On any interval of this type, I approximate by this value, that is the value of the process at the left part of the interval. And I have a sum here that is from k equal to 0 to n minus 1. So are you okay the way I have built my approximation? On any interval of this type, I approximate my process that is in white here by its value in the left part of the interval. And I obtain in this way something that is piecewise constant. Okay, I have this one. We are going to prove two things. First, that on 0 capital T, this approximation converges toward my stochastic process xt. But it is a real approximation, and when the step size of my interval goes to 0, okay, I converge toward x. It's the first thing we are going to prove. In a second step, we are going to prove that the process defined this way is measurable in the sense of this definition. If I prove these 2 points, it will prove that since I know that measurability is preserved by passing to the limit, if this one is measurable, if x is the limit of this one, then I will have the measurability. Okay? So it's what we are going to do. So to prove that x and t converges toward xt. For example, we can consider the difference. Okay? So first step, we are going to prove the following one, that the infinite norm of xn minus x, okay, on 0 capital T, converges toward 0, P almost surely, that is for almost sure, for almost all W in omega, when n goes to plus infinity. So let's have a look on the difference here. X and t of W minus xt of W. So x and t is written as a sum, okay? I can decompose this value here using the element of my sum. And what I can do, I can write it this way. It's the sum from k equal to 0 to n minus 1, indicator function of kt over n, k plus 1 t over n of t x k t over n w minus xt over w. Here I have just done the difference between my approximation and my true process. I obtain this one. I just write this one, decomposing on all the little intervals I have considered. And my job is to prove that this one goes to 0 when n goes to plus infinity, in fact independently of t. Are you okay with what I have written? I have x and t here, and I do the difference. So the term dealing with small t equal to capital T disappear because at the end both of them coincide. Okay, so it remains what happened on these intervals here, and I just do for each interval the difference between my process and the value of my approximation on this little interval. Okay? So do you have an idea to prove that when n goes to plus infinity, this one goes to 0? In fact, you see that, in fact, this quantity is related to a time t that is in this interval. In this interval that becomes arbitrarily small when n goes to plus infinity. So it means that t and kt over n are close together. Okay? I know that t gives xt of w is continuous with proba 1 on the interval 0 capital T. What can you say about a continuous mapping on the interval 0 capital T? Continuous mapping on the closed interval of the form 0 capital T here. In other words, what is to be continuous on the compact set? Morning. I'm agree. And also continuous on the compact set means okay, I am bounded and I reach my bounds, okay? I'm agree with this. Yeah. And also, uniformly continuous. If I am continuous on a compact set, I am uniformly continuous. And what is the meaning of being uniformly continuous? It means that I have the continuity property, but independent of the point I choose. Okay? It just depends on the length between 2 points. So what is the meaning of this one? For all epsilon strictly positive, there exists an eta that is strictly positive, such that t minus t prime strictly less than eta implies xt of w minus xt prime of w less than epsilon. And it just depends on the distance between t and t prime, not on the specification of a fixed time. This is the uniform continuity that implies the continuity. But if I have a look on what I have before, I see that what is the distance between t and kt over n? T belongs to this interval, so I know that the distance between t and kt over n is less than, let's say, capital T over n for sure. Capital T over n that may be made smaller than eta for big N. So if I consider n big enough in such a way that the size of this interval is less than eta, and it's possible because the size of this interval is capital T over n, I have here the distance between points that will be less than this one, and so the distance between the images by the stochastic process that will be less than epsilon. So I can say that, from what I have written here, that in fact the maximum of xn minus x, taking the maximum over t, because I have something that is independent of my point, okay, will be less than epsilon for big N. I repeat my argument. My arguments tell me that if I want to control this term, I can do it from the uniform continuity because I know that the time here and the time here, because t belongs to this interval, the distance between the two instants is less than capital T over n. So if I take big N, n big enough, t and kt over n will be less than eta, so this term will be less than epsilon, so all this term will be less than epsilon, and I have the sum of indicator function here that is equal to, in fact, on 0 capital T, that is equal to 1 almost surely. And so I have proved what I want, that is, for any epsilon, if I take big N, n big enough, this is less than epsilon. This is exactly the definition of converges towards 0. And why P almost surely? Because the continuity is true for P almost all W. So I can do my reasoning for a set of W that has a probability equal to 1. Okay? Question? Theta. Theta. Eta, il dépend de... Oui, oui. But P almost surely, I have a set of omega of proba 1. Okay, I am agree with you that here I depend on omega, but I know that this argument is true for a set of omega with proba 1. And it's what I want to prove here. I want to prove that I have this one, that is, for a set of omega with probability 1, I want this difference goes to 0 when n goes to plus infinity. Exactly what I have proved here. I don't say that it is not uniform in W or in omega. Okay? It is uniform in time, not in W. This one is the maximum over 0 capital T of this one. Omega, I don't know it. I don't know what is the structure of omega. Huh? I don't know if there is an infinite norm or not on omega. I just work on the time. Okay? Do you agree with what I have done? So I repeat after I answer to your question. I have my process X. I approximate it using this idea by stepwise function. How to do? I consider a subdivision. On each element of my subdivision, I approximate my process by the varying at the right part, the left part of the interval. I obtain this approximation. First, my job is to prove that this one converges toward what I have in white here. I consider the difference between them. I write it using sums and my indicator function of my subdivisions interval. And I remark that I have this one. But what happened? In fact, I remark that T and KT over N are close together. The maximum of the distance is capital T over N. That is something that may be made as small as I want, independently, okay, of K. Independently of K. Why? Because I use the uniform continuity. If I am continuous on a compact set, I have uniform continuous, that is this one. So if 2 points are close together, the same will happen for the images by this mapping. Exactly what I have here. T and KT over N are in absolute value less than capital T over N. If I choose N big enough, I will be less than my eta, and so this one will be less than epsilon for any K. Any K. So that's why when I do the sum, all this term will be less than epsilon. I will have the sum of my indicator function that will be 1 almost surely for T belonging to 0 capital T here. So I have this. This one that is less than epsilon for big N. That is exactly what I want to prove. So Xn converges toward X when N goes to plus infinity in the sense I have written on the board. That is now, in order to prove that my X is measurable, the only thing I have to prove is that Xn is measurable. Xn is measurable. And if it is the case, if I am the limit of a sequence of measurable terms, I am myself measurable. I approximate, I prove that the sequence, the element of my sequence of approximation are measurable, and I will do the job. So the only steps it remains to prove is that this one fulfills this one. But now it won't be complicated to do this, because I pass from something that may be very complicated to something that is piecewise constant. So I simplify greatly the problem here. Question? Other questions? So I erase the first point, and now my job is just to prove that if I plug inside the definition, I replace xt by xnt, I have what I want. Okay? And you will see that it is just coming from the definition of xnt that is piecewise constant. Question? I don't know the name from question? No. So may I erase this? I have the convergence using a uniform continuity argument here, because the trajectories are continuous on compact sets. Okay? I repeat, may I erase? Everybody? So second step here, I want to prove that x and t t belonging to R plus is measurable in the sense of the definition I have kept on the board here. But let's see what I have to do. I have to study the following. Okay, I have to study this set here. But here, I repeat, it's not that complicated because I know exactly what are the values of my process, okay, on each little interval here. So typically, if I suppose that my time t is in 0 t over n, what is the value of xnt in this case? It is x0. So I have this one. 0 t over n times x0 minus 1 of b. It is this set when t belongs not to 0 capital T but to 0 t over n. I continue. Disjoint union of what? T over n, 2t over n, time what? On this interval, the value of my process is xt over n. So it's time xt over n minus 1 of b until union. So for the last little interval, that is n minus 1 t over n t time the last for k equal n minus 1 is x n minus 1 t over n minus 1 b. So it remains the last term, that is the term for t equal to capital T. And so I have capital T times x capital T minus 1. Are you okay with this equality here? So it means that I want to decompose the set I am interested in, okay, considering that for particular value of small t, I know exactly what is xn. By the way, I have built it. I have a particular value between 0 t over n, I have a particular value between t over n and 2t over n, and so on, until capital T. So if I am interested in this set, first I look what happened on this little interval here. So I consider the time to be here, but if the time is here, what I have here is simply x0. So I am interested in x0 belonging to b, that is the preimage of b by x0. I do this for all the little subinterval until the end, and at the end what I have? At the end I have just capital T, single time, and here I have xt, x capital T, so x capital T minus 1 of b. And now what happened if I have a look on this one? But I know that this one belongs to the Borel sigma algebra of the interval 0 capital T. I know that a stochastic process is a family of random variables. So x0 is a random variable. So x0 minus 1 of b belongs to A. And so on. This one belongs to b of 0 capital T. This one belongs to A. At the end, I have terms that are terms of the form a Borelian of 0 capital T time an element of calligraphic A. I do a union of such term, and so I obtain something that is, by construction, in this sigma algebra. So a process that is stepwise constant is measurable. You have the proof on the board here. And since I have proved that my piecewise constant sequence converges toward my stochastic process X using the continuity argument, I have proved that continuous for a stochastic process implies measurable. Okay? I will use 2 or 3 times in this course this kind of approximation. So have a look on this one and keep in mind that I consider subdivisions and approximate on each element of my subdivision a process or a mapping by the value at the left part of the interval. So I repeat that at the end, when I have obtained this decomposition through the definition of my approximation, I obtain for each term here an element of the sigma algebra times an element of the sigma algebra. So all of them belongs to this sigma algebra, and by union, the union is still in my sigma algebra by the properties of a sigma algebra. So keep in mind what that continuous implies measurable. And typically, if I know that a process is measurable, I won't need to use this kind of definition. Continuity will be enough. And to prove continuity is in general, okay, in general a little bit less abstract than to come back to this definition of measurability. Okay? Do you have questions? Yeah? So, if you want, here I fix it because my definition is this one here. Okay, so if you have a look on the definition of measurability, for any t, I need to have this one. Okay, for any t. So I fix a t, because it's for any t, and once I have fixed a t, then I do the job here. Okay? It's not, it has to be true for any t, but I do the proof guide. I fix my capital T, and then do the job. Because what I have to prove at the end is just that this set belongs to the sigma algebra. Okay, so I do it, I do this proof, doing what I have done. Okay? I do a capital T by capital T reasoning, and it means that my approximation changed with capital T. Because if capital T is bigger, I will have more intervals in my subdivision. Other questions? No? So, to summarize a little, I have defined several types of equality for stochastic processes. Equidistributed, version of, indistinguishability. When I have continuity, the two last coincide. Okay? So to say that the probability that xt equal to yt is equal to 1 is the same that to say that the probability of the intersection of the sets xt equal to yt is equal to 1. Equivalent when I have continuity. So continuity will allow us to work with the definition of being a version of instead of being indistinguishable, something that will be more easier to handle. Okay? Second step, at this stage I have introduced one notion of measurability, this one. That is just the analogous of what we know in the case you have two variables. Omega here and the time. Okay? Once again, I have a definition that is a little bit tricky to handle, but I said that, okay, in the case when I am continuous, as a stochastic process, that is, my trajectories are continuous on a set of for P almost all W in omega. But in this case, I am measurable. Okay? So instead of working with this one, we will work with the notion, classical notion of continuity, trajectories by trajectory. Something, once again, that is easier to handle. Okay? So it remains 10 minutes. What can I do? So maybe just introduce a definition. Yes, to finish the part 0.5.1, okay, the introduction of stochastic processes. So, next week, okay, before to introduce the last definition, next week, okay, I will do the same. So that's why we need to spend time on thinking about what we have seen today. Because in fact, you see that here, my sigma algebra here is completely independent on capital T. I have the same sigma algebra here independently on the capital T of the capital T I have here. The next definition that we are going to introduce is the fact that we can make this definition compatible with here a family of sigma algebra evolving with capital T. From a financial point of view, what may be the interest? The financial interest of this one is that if you have a fixed sigma algebra, intuitively it means that you have a fixed amount of information. And in general, in real life, it's not what happened. Typically, for financial problems, you have information that increase across time. In maths, okay, it's something that we are going to modelize by the notion of filtration, increasing family of sigma algebra, representing the fact that when the time increases, I have more and more information. And in fact, this notion of filtration will be plugged inside this definition to have a notion of measurability that is compatible with the fact that information is not fixed in financial market, but involves a long time. Okay? So that's what I want you to focus on this for next week, okay, to be clear with this definition, because we are going to complexify a little the things. Okay? Not that much. If you have understood this one, it's not that different, okay? But it's what I want you to have in mind. Okay? So take time on the proof we have done together. And after it will be better. Okay? So next session will also be a little bit hard, okay? And after it will be a little bit less technical. Okay? But I finish with the definition in order to conclude the part I have started here. So may I erase everything if you don't have questions? And think also about this approximation, because it's something that we are going to use several times, especially next week. Questions? C'est la définition d'être mesurable. Oui, oui, c'est la même chose. C'est juste, ça c'est considérer la préimage du processus stochastique. D'accord? C'est ça la préimage. Là tu as en fait x moins 1 de b, où x est le truc dépendant des deux variables. Okay? So I erase just the last definition that is a more classical one, okay? Just to say what? But that now we are going to work most of time with families of random variables, what I have defined as a stochastic process. And we are going to define here a subset of these stochastic processes that is a kind of, not a kind, an L2 space. L2 space, okay, as you know for the random variables. So it is the last definition for today. That is this one. So the definition 0.5.7. Okay. I will denote by L2 of omega times 0 capital T. In fact, it's an L2 space as usual. The only thing, once again, is that my universe is just the product of two sets. This one, okay? So what is L2 of omega times 0 capital T? It will be the set of the xt, t belonging to 0 capital T, and I want them to be measurable, such that, so in L square, okay, I have random variables in general with the expectation of the square that is finite. It's what I have inside. But here, keep in mind that I have two variables. So by the expectation, I mean the expectation related to the probability on this product space here. And what it will be, that on omega, I have the classical expectation, and on 0 capital T, I will have the Riemann integral. Okay? So such that the expectation of the integral of the square is finite. So it's L2 of omega times 0 capital T. So the classical definition you have in mind for L2 of omega, just adapt it to the case that I have two variables and not a single one. So here I have just the expectation of the square, considering that I have a product of spaces here. Okay, so my expectation has two parts. The expectation for this one and the integral for the parts dealing with the variable 0 capital. So, as usual for L2 spaces, okay, just using what I know from probability theory, I can say that as all the L2 spaces, this one is an Hilbert space. So what is an Hilbert space? I remind you that it is a complete vector space that has a scalar product. And what will be the scalar product this way? Well, the scalar product between x and y in L2 of omega times 0 capital T will be what? Well, you have here, in fact, the square of the norm here. The scalar product will be the expectation of the integral between 0 and capital T of xs, ys, es. So the scalar product on L2 of omega times 0 capital T, you have two variables, the time and inside w related to the expectation capital T. Okay? So I will denote by this one the set of the measurable stochastic process as defined today that are square integrable in the sense of the product measure on this space. So the new expectation becomes the expectation of the integral. Okay? So see you next week.